This is applied research, and now we're going to talk about bivariate analysis as well as do your exercises. So let's begin with the cross-tabulations in chi-square. So far, the methods that we have used have only allowed us to look at the frequencies, to look at our measures of central tendency, such as the means, modes, and medians, and to look at the measures of dispersion, such as standard deviation and z-scores for the one interval or ratio level. And remember, those are continuous and numerical variables. That's why we were able to use the measures of central tendency, frequency, and z-scores on those. When we use bivariate, bi means two. So it's allowing us to look at relationships among two variables, to look at measures of the strength of the relationship between those two variables, and to test the hypotheses about the relationships between two nominal or ordinal level variables. Just to review, nominal and ordinal, those are categorical variables. They're not numerical. So it would be something like testing the relationship between gender and the type of crime committed, or the level, college level, and socioeconomic status. Not looking at income, because that would be looking at numerical. So remember, we're looking at categories here. For example, what does this table tell us about opinions on welfare by gender? Take a minute to look us over, because we've got categorical variables, male and female. Remember, we could label these 1 and 2, but we don't need to for the purpose of doing bivariate statistics. So we're looking at whether or not males and females support cutting welfare benefits for immigrants. When surveyed male, we're surveyed 25 of each. 15 said yes, 10 said no. Females, 5 said yes, 20 said no. So what can you conclude by that? That males support cutting welfare benefits more so than females. Are frequencies sufficient to allow us to make comparisons about groups? What other information do we need? Frequencies just allow us the number of occurrences, but it doesn't allow us to make those comparisons about groups. When we look at this table, as we talked about in class, this one is more helpful, because now we've got percentages. So just telling us the number wasn't enough. And these are very simple numbers, but when you're looking at a large number of results, if you were looking at something that had a lot more categories than this, and you would have to calculate it all up, and all you had was frequencies, it wouldn't mean very much to you. But when we look at it this way, very quickly you can tell that 80% of the females said no, opposed to 40, twice the amount. And there you go, you got 60% of males said yes, where only 20% said yes for females. It tells you a lot more information. How would you write a sentence or two to describe what is in this table? I just really went over that. Females are more likely than males to disagree on increasing benefits for immigrants. Males are more likely than females to recommend decreasing benefits for immigrants. You can do it however you want within your sentences. You can even use the percentages within a sentence, that males are twice as likely to want to reduce benefits for immigrants. Cross-tabulations. This is what we were using. Really, when we have these tables here, we're cross-tabulating. That's what this is. So we either are going to calculate either the column or the row percents, Our calculations are the number of frequencies in a cell of a table divided by the total number of frequencies, right? Right here. That's where we get this. And all percentages in a column or row should total 100%. Now we're talking about percentages. We're not talking about rates. Remember when we looked at rates, rates will never calculate all the way to 100. So we look at this example. Here we have social work degree, and we're looking at the types of degrees, and we're looking at, again, male and female. So here we're told 20 of males have a BA, and 30 have an MSW, and 10 have a PhD. So how did we get those percentages? We divided. So you would divide your 30 by 60, and you're going to get 50%. And the same thing over here. You're going to do 20 by 100, and you're going to get 20%. So what group had the largest percentage of PhDs? Okay, let's go back. Which one had the largest group? If you look at it, they both had the same number, but males had a higher percentage of PhDs because we're looking at less males. So if we answer that, what had the largest percentage? Well, your percentage would obviously be males. What are the ways in which you could find the missing numbers? We just did that. I mean, there's a number, right? You could subtract, divide. So either way. Is it obvious why you would use percentages to make comparisons among two or more groups? What do you think? Do you think this is easier to look at the percentages? If you look down here, if you had seen 10 and 10, you might think that the same percentage of that group were PhDs in the same number, but no, you have more males that were PhDs. Just tells you a little bit more. So another table where people with drug, alcohol, or a combination of both most likely to be referred for individual treatment. Here again, we're getting into more rows and more columns, and so it becomes more difficult to just look at frequencies. So if we look at the services, and we look at alcohol, drugs, or both, individual treatment, group treatment, AA, and a total. So we have a total of 40 alcohol that have been referred, 50 been referred for drugs, and 10 for both. So how much more likely are people with alcohol problems alone to be referred to AA than people with drug problems or a combination of drug and alcohol problems? So let's go back and look at AA. So we see that those with alcohol are 50% more likely to be referred than in drugs at 20 and both at 30. So it answers your question very simply. This right here is what you would see in an article. If you can understand this, you can read any article. So we use cross-tabulations when we want to look at relationships among 2 or 3 variables. We want a descriptive statistical measure to tell us whether differences among groups are large enough to indicate some sort of relationship among variables. Now, remember at the very beginning we were talking about bivariate. So bivariate is among 2 variables. When we start getting into 3 and more, we're looking at multivariate, but you can still use the cross-tabulations. So we would not use crosstabs to tell us the strength or actual size of the relationships among 2 or 3 variables, to test a hypothesis about the relationship between 2 or 3 variables, or tell us the direction of the relationship among 2 or more variables, or to look at a relationship between one nominal or ordinal variable and one ratio or interval variable, unless the range of possible values for the ratio or interval variable is very small. So what we're looking at here, go back, these are just cross-tabulation tables. They are not telling us anything about a relationship yet. This is just strictly descriptive. So we can use crosstabs to visually assess whether independent and dependent variables might be related. it doesn't tell us anything about the strength. It just shows the type, if there is a relationship. In addition, we also use crosstabs to find out if demographic variables such as gender and ethnicity are related to the second variable. For example, gender may determine if someone votes, Democrat or Republican, or if income is high, medium, or low. Ethnicity might be related to where someone lives or attitudes about whether undocumented workers should receive driver's licenses. These are just examples that you can find out from a survey and by using crosstabs. So we use tables in these ways, and we can set up some decision rules about how to use them. So this is just standard practice. Independent variables should be column variables. Okay, where's our columns? Okay, there's our columns. So there are independent variables. If you're not looking at independent variable relationships, use the variable that can logically be said to influence the other as your column variable. That's the same thing. So if you really don't know yet and you're just really running crosstabs to see what your frequencies are and your percentages, then it doesn't matter. You just need to make sure that if you have one that you think is going to influence the other, that's your column. So using this rule, always calculate column percentages rather than row percentages. Use the column percentages to interpret your results. And that's what we did here, right? We have column percentages, because going the other way is not going to tell us anything. Okay, for example, if we were looking at the relationship between gender and income, gender would be the column variable. Let me see if it's here. Okay. What I want you, let me do something. Okay, I'm going to jump over here to this, that I've drawn this. So if we're looking at the relationship between gender and income, gender is our column variable and income would be the row variable. So now think about this. Logically, income does not determine whether you're male and female, but a male and female may determine the income. So obviously these are going to be, whatever you deem it to be. And then you would, go through and add all the way down. You would need another row here for your total. So your total would go down. Okay. Here, if we were looking at the relationship between ethnicity and location of a person's home, ethnicity would be the column variable. So if we're looking at ethnicity and location, of course you would need more columns, but here you would have your ethnicity as your columns, and the location of a person's home would be your rows, because location doesn't determine ethnicity. Now, if we are looking at the relationship between gender and ethnicity, one wouldn't influence the other. So because of that, they can be either one. We can switch these over and put them here, like here. We could take those out, make this male, this female. So they could be either one, because neither one is influencing that. Now, something important, this square right here, this is not, you wouldn't put gender here to go across, and you also wouldn't put ethnicity here either. This is really, you would put the relationship between the two. So you might do, ethnicity and then gender. So it's both of them. And then if you wanted to, you would put a column above that to say gender, and then over here, a column over here that would say ethnicity. And something nice that I've already mentioned to you, that you don't have to do these columns by hand or in Word. When you use SPSS or another software program, when you choose what you want to be your column and what you want to be your row, and it will pop out your table. And it'll include, right here where it says include percentages, you can include percentages, you can include ratios, you can do percentiles, whatever you choose when you run SPSS. You don't need to know how to do that now. Now, if we want to do additional work, we have to use what's called our chi-square statistic. Now this too is a bivariate. So we're going to test a hypothesis about two variables. We're going to look at the strength of a relationship between an independent and a dependent variable. So we've moved from our correlations now to our strengths. So we're going to determine whether the relationship between the two variables is large enough to rule out random chance or sampling error. Remember what we talked about, our sampling error? We want to make sure that the relationship between these variables is from an impact from the relationship between those two, in that the outcome is not due to some other reason besides those two variables acting upon each other. So chi-square is simply an addition to the cross-tabulation, and it will give us more information about the relationship. Remember I brought it up that you're going to see a chi-square number, a result, but that doesn't mean anything if you don't know the criterion chi-square statistic. So, but it does not provide any information about the direction of the relationship between the two. And you'll understand that more when we do an exercise here in a few minutes. But it doesn't tell us whether it's positive or negative relationship, meaning does one go up and the other go up, or does one go up and the other go down? Same thing. That's all right. So let's use the following table, and we're going to test a hypothesis using chi-square. So as you'll notice that there's a couple empty spaces. They are not filled in because there's two concepts that need to be addressed before you do the calculations. I'm going to go over these, but this is not something you need to walk away with knowing, because we're not actually going to compute the statistic. So you're more concerned with how to read that table. But degrees of freedom, in any table, there's a limited number of choices for the values in each cell, right? You can't have 100 here. So there's only a limited number, and that's your degrees of freedom. Your marginals are the total frequencies in the columns and the rows. Okay, let's look at this. So let's look at the number of choices we have in the previous table. So the table becomes this. Let's go back. Here we know that this is going to total to 50. So you can guess that that's going to be what, 10? And here again, this one, total over here, is going to total to 50. So if we fill that in, look what we have. The rules for determining your degrees of freedom in these cross-tabulations or contingency tables, they're called either one. If any two by two tables, that means you have two columns and two rows, right here, two columns, two rows. We're not counting your totals. So the degrees of freedom equals 1. Two columns, two rows, degrees of freedom, 1. Now remember, let's go back here real quick. The marginals is just the total frequencies in columns and rows. These are your marginals. I don't know why they don't call it totals, but we're going to call it marginals. So any 2 by 2 table, degrees of freedom is 1. This is only important if you had to look up a statistic in a statistical table. So this is why you don't have to know how to calculate this, but it's just nice to know you were told about it. So for all other tables, you calculate your degrees of freedom as C minus 1 times R minus 1, where C is the columns and R is the rows. So for a table with 3 columns and 4 rows, so simple math, you just substitute the C with a 3, the R with a 4, and do your addition. 3 minus 1 times 4 minus 1 equals 2 times 3 is 6. So your answer is 6 degrees of freedom. Like I said, you only need that if you have to look in the chi-square table. And we don't have to do that normally because we have SPSS that does it for us. So the importance of the degrees of freedom. As I said, you will see degrees of freedom on your SPSS printout. Most types of inferential statistics use degrees of freedom. Remember, inferential statistics is using statistics to predict an outcome in the future. So in chi-square, we need to know the degrees of freedom if we are calculating it by hand, and you must use the value of chi-square and degrees of freedom to determine if this chi-square value is large enough to be statistically significant. That's where that table comes in. So we would have to consult the chi-square table that's available in most books, and it's available in the back of your book as well. So you can, if you knew the value of chi-square and your degrees of freedom, then you can find whether it's significant or not. So, okay, what we're going to look at now is if you have a hypothesis and testing a hypothesis, how would you go about doing that using chi-square? So in your own study, if you are looking at two variables, as we mentioned here, okay, two categorical variables, then you would use chi-square. So in order to do that, if you're not using chi-square, you really don't need to know any further right here within your own study. Of course, it's good to listen to it. So if you're testing your hypothesis, the first thing you do is you state your research hypothesis. You state the null hypothesis. You're going to choose a level of statistical significance, which is also called the alpha level, where you have the little upside down little a that runs like that, and that will tell you your statistical significance. And remember, we chose this, so you might be choosing 0.01, 0.05. That's the level that you want to reach. So you want to select and compute this test statistic. You would do that within your software program. Then you're going to make a decision regarding whether or not to accept or reject the null. That's really what we're doing in every experiment, every research. We're rejecting the null. And when we reject the null, what are we doing? We're accepting the research hypothesis. Okay, I'm not going to go over that. Okay, let's just look at the first steps. So a hypothesis is there's a relationship between income level and education for respondents in the survey. The null hypothesis, there is no relationship between income level and education. So we picked our confidence level is set at 0.05. That's our statistical significance. So that means that we are saying that we are with 95% certainty that it's going to be correct. So if it's significant, it's going to fall below 0.05. Okay. Using the chi-square statistic must be large enough to verify a relationship. If you were doing it by hand, which we don't ever do anymore, we would compute it and then check the table, and it has to be equal or larger to be significant. We use SPSS, and on the printout, it's going to tell us our significant value. Okay, let's look at this table here. We're not really going to calculate chi-square, but I just want you to see what the result is. Because you would have something like this in a research project, a research study, and it might have this exact table, and then over here might be another column that says your chi-square as well as your significant level. So for this table, let's go back here and look. If you need to, write it down. For that table, the degrees of freedom is 1. Remember, it's a 2x2 table. The alternative hypothesis, receiving service is associated with location of residence. Look back and look at that. Service and location of residence. Service, yes or no. It's not saying a type of service. It's saying whether or not they receive service. Okay. The null hypothesis would be what? There is no association between receiving service and location of residence. Okay, we don't want to go over that. Okay, this is important. This is our SPS printout. This is what you would actually may even see in a research paper. So if you find an article that's using chi-square test, this is how you would explain that. Okay, let's look at the printout. This is what you would happen when you do a chi-square result in SPSS. But what's more important is this is many times reported pretty similar to this in an article. So you would have your Pearson's chi-square. Now see here, it is telling us what our result was 2.56. The likelihood ratio, that's the criterion that you're trying to result in higher, is 2.59. This is only normally reported in SPSS. Many times in an article you won't see this likelihood ratio. What you would see would be this, your degrees of freedom possibly, and then your test of significance. It's telling us this is not significant. It's not anywhere near. So it's all that you would report here, and you can see it here too. This number is smaller than this number. So you know just by looking at it, it's not significant. But that's the result of the test of significance is 0.76. So we would report that this is not a significant result, that we cannot say that there's a relationship between those two variables. Okay, now we're going to move to the exercise. Now, I want you to get this document. It is in Blackboard under week 4, right where this recording is. I want you to pull this up, and I want you to review and read this page, and then we're going to do the next page, which is going to be some actual factual questions and exercises. So there's no reason for me to read this to you. It's really much what we talked about. Pearson's R. The one thing that it is important is the relationship is inverse or negative when Pearson R is negative. So that means that one goes up and the other goes down. In an inverse relation, I'm sorry, back up. That means when those with the high scores on one relative have low scores on the other. What I said. In an inverse relationship, the closer it is to -1 means the stronger the relationship. And when you look at the opposite, when you have a positive R value, it means the relationship is direct or positive. So those with high scores will also have high scores on another. So that means that it's a positive value or a direct relationship. Just read this area down here, and after you have read that, we'll go over the table. So what you're seeing here is a bivariate correlation table among all the variables, and there's different ways. If you notice that they put ones here and then the label across here. You could, it just takes your table really big, but you could have just go ahead and written in community violent exposure here, bullying by peers here, and so on. So when you're looking at this table, and hopefully you're looking at it, you've printed it off or you have it on your computer, so it's a little bit bigger than the way it is there. But you look at the comparison. So you've got the relationship between 1 and 1. It's always going to be perfect. So that's why it's not there. It's just expected. So the relationship between 1 and 2, so it'd be between community violence and bullying, is 0.20. The relationship between community violence exposure and SAT 9 mathematics is negative 0.24. So your community violence exposure with number 4, which is your reading, is negative 0.14. And notice the negatives as opposed to the positives. And then the last one, number 5, is the community violence exposure in its relation to the GPA. And there it's a negative 0.26. The reason that only half the table is there is because it's redundant. It'd be the same thing. Putting 1 here and putting down here with bullying with peers is the same thing that's right there. So there's no reason to list it. You'll always see bivariate correlation tables just like this. Now what I want you to do is to pull up the other paper, the exercise questions, and I want you to answer these as best you can. And they're not, if you can do this, you can do bivariate correlations. Okay, this is how simple this is. So go ahead and fill this out, and I'm going to go over it. So obviously stop the recording, and then when you finished it, start it back up, and I'll go over the answers. The first one, what is the value of the correlation for the relationship between variable 1 and variable 2? Simply look at, let me stop this for a sec. Oh. Okay, let's look at the table here to find the answers. I'm not going to switch back and forth, so you can have printed off the questions would be much easier. So on the first one, what is the value of the correlation for the relationship between 1 and 2? You find it, in fact, it tells you where to find it. The answer is 0.20. What is the value of the correlation between mathematics and reading? It's going to be right here, 3 and 4, 0.60, a positive direct relationship. How many of the 10 relationships in the table are inverse? Simply count the negatives. Negatives are inverse. Count those up, you get 6. What's the value of the correlation coefficient for the strongest relationship? Find the one with the highest. Doesn't matter if it's negative or positive. So the answer would be 0.64, so it's between math and GPA. Which one of the following pairs of variables has a stronger relationship between them? So we look at both of them, community exposure and bullying, which is right here, 0.2. Community exposure and math, which is 0.24. That one is stronger. And remember, it doesn't matter if it's negative or positive. This means that there's a stronger relationship between those two, even though it is an inverse relationship. Means that as community violence exposure goes up, math goes down. The next one, which one of the following pairs has a weaker relationship between them? We look at math and reading. We know it's 0.60. Math and GPA is 0.64. That one right there has a stronger relationship. The correlation coefficient for the relationship between bullying by peers and GPAs is way over here at negative 0.25. And, the correlation between these two indicates what? Negative 0.25. Well, it's an inverse relationship. So one goes up, the other one goes down. So it would be B. Number 8, the correlation relationship between math and reading, which is right here. It's a positive relationship. What does that tell you? That tells you that those who are higher in math tend to be higher in reading. It's a positive. One goes up, so does the other. Now, what is the weakest relationship of these? It would be negative 0.07. And even doesn't matter again, negative or positive. Anything that's below 10 normally is very weak. A lot of times it depends on where your interval is. You can do it, it's 0.20 and down, and it depends on many times the type of statistics that's being used. But anything below 10 is low, is a weak relationship. Okay, next we're going to do an exercise for chi-square, and I want you to do the same thing. I want you to read this page, and then I want you to complete the other page that has the exercise questions, and we will go over the answers. Also, too, make sure you check Blackboard, because you've got 3 other exercises that I want you to complete before class, before the 5th class, and I want you to bring them to class. So we will go over the answers there. So there'll be one on sampling bias, there'll be one on correlation, and one on chi-square. And then in class on Monday, the last class, I've decided there will be no final exam, but we will do more of these exercises on the multivariate statistics. We'll look at t-test and regression, and we'll do exercises just like these right here that you're looking at, so that you don't have to calculate. We're not going to do that. We're going to do this. So read this, and then we'll do the next page. Okay, I want you to do the same thing here that you did before, that I'm going to go over the answers to the questions, but I'm going to go back to the table. So it's much easier than switching back and forth. Oops, that's the coefficient. Oops. Okay, I want to go over a little bit of this right here. This is what you would normally see in a research article. This is where you would see the explanation. This information is coming from this table, but even though you don't see where it says a total of 105 young adult parents, because these are percentages, you could figure out, knowing this information up here, you could figure out the number from the percentages. So there's not always, the information that's talked about in the article is not always in the table, but what is normally talked about is what they had found to be significant. So first, look up here, because I don't know if we've discussed this. The chi-square is the difference among frequencies, and it's symboled by chi-square right there. The null hypothesis tests that a difference was created by random sampling error. So we do our significant test at any of these three levels. Obviously, it's more significant if it's at this level than this level. Also, too, if you'll notice that they reported the chi-square in the text, but not in the table. So they're explaining it to you that the participants were more likely than young adults to rank the roles of religious guide, where does it, right there, which is significant, and it's telling you it's significant at the 0.001 level right there, and family historian, and they're giving you the chi-square value. So you know that the criterion chi-square was lower than that. It had to be, otherwise it would not have been significant. So right there doesn't really tell you anything, except for we know that it was significant. So now let's answer those questions. The first one, what percentage of grandparents thought the role of being family historian was important? So very easy. Family historian, you just use the table. Go over to the percentage of grandparents. Whoops. I'm sorry. Family historian. I wrote down 60. So the answer is 64. Family historian right there, 64. So the smallest percentage of grandparents regarded which role as important? Well, grandparents over here, 28. So chauffeur. Based on the information, how many null hypotheses should be rejected? Well, any of those that were not significant. That means that you reject the null. 6. Is the difference between parents and grandparents on the importance of the role of a friend statistically significant? If yes, at what probability level? So you find friend. Well, first of all, we already know it's not significant, so the answer is no. Is the difference between parents and grandparents on the importance of the role of a playmate significant? Well, yes, we know it is. And we look at our key, it's by 0.001. Should the null for the difference between parents and grandparents on the importance of the role of teacher be rejected? Why or why not? Yes, it should be rejected because it is not significant. And that's all you need. It is not, the results showed that it is not statistically significant, therefore we reject the null. Number 7, the difference between parents and grandparents is more highly significant for which of the following roles? So you look at friend, it's not even significant, so we're not even going to look at it any further. Family historian and religious guide. So we look at these two. These numbers over here don't really tell us anything about that. We're going to look at our significant level. So religious guide is at 0.001, which is more significant than family historian. The next question asks the difference between significance for playmate, family historian, and role model. Well, let's look at family historian. Role model's not significant. We don't include that. Family historian or playmate. So we look at the significance level. The answer is playmate. The next question on your your exercise, I want you to answer and bring to class on Monday, and we'll just talk about that. And that's going to conclude all that I'm going to go over for bivariate statistics. This is what we were going to do in class on Monday. So by you listening to this, as well as I have some other exercises that I'm going to post, one, as I said, one for chi-square, one for bias and sampling, and one for correlation coefficient. You are to complete those and bring them to class on Monday. Since you've got 4 hours open on Monday, that's what I had planned for you to do during that time. Also, too, I'm going to be posting an article that I want you to analyze that will be due at the end of the 5th week, I think, is when I'll have it done for you. But I'm going to post that in week 4 for you to read and begin to analyze.